Hey everyone, this is a continuation to our applications of parametric differentiation, and we're going to talk about stationary points. With y equals to sine 2t and x equals to e to the power of t bracket t squared plus 1 whole thing square, and that t is between 0 and pi inclusive. The question is that to find the coordinates and the nature of the stationary point. So nature being, is it a maximum or minimum point, or is it just a stationary point of inflection? Because we're dealing with stationary points, we are going to look at dy dx equals to 0. And of course, nature, therefore first or second derivative test. Right, now, first of all, we just find dy dx, alright? So dy dx equals to differentiate sine, it becomes cosine 2t, differentiate inside 2. Now I differentiate x to power with respect to t, therefore I differentiate e to the power of t first, giving me back e to the power of t. Therefore, I just times the other term. Now I just differentiate the other one, which is t squared plus 1 whole thing square. Bring out the power, reduce the power by 1, differentiate inside, then I finally times the other term. Simplifying, I will get 2 cosine t over e to the power of t, t squared plus 1, t squared plus 1 plus 4t. So this is our dy dx. Now we let it become 0. Which means that, sorry, this is 2 cosine 2t. 2 cosine 2t equals to 0. Cosine 2t equals to 0. So we know that t is between pi and 0. Therefore, 2t will be between 0 and 2 pi. Therefore, 2t just has pi over 2, 3 pi over 2. Because 5 pi over 2 will be more than 2 pi. T is there equals to pi over 4 and 3 pi over 4. So yeah, there we have it. We have two stationary points, but we want to find the coordinates, right? The x and y coordinates and the nature of the stationary point. So we know that this is our stationary point. Now it's time to find the nature. Nonetheless, we want to find the coordinates first. So we have t equals to pi over 4, y equals to sine pi over 2, 1, x equals to e to the power of pi over 4 bracket pi square over 16. So be careful, pi over 4 whole thing square is pi square and then 4 square in the denominator. So that will be it. T equals to 3 pi over 4. Y equals to sine 3 pi over 2, which is negative 1. X equals to e power of 3 pi over 4 bracket. Now it's 9 pi square. 3 pi whole thing square is 9 pi square. Again, 16, again, plus 1 whole thing square. Now, let's consider second derivative test or first derivative test. If you think about it, second derivative test involves d2y dx2, right? So, d2y dx2. Is there a way to obtain d2y dx2 here? Answer is no. You cannot just differentiate with respect to t again, because if you want to differentiate this function again with respect to x, it's going to be very difficult, all right? Because you have to go and times the dx dt throughout here, and I'm pretty sure you don't want to do that when the dx dt is this complicated, aka this one. Furthermore, you can't just simply take d2y dt2 over d2x dt2 and then claim that it's d2y dx2. It's not. Okay, it's not. If you look at it, d2y below d2x, it won't give you back d2y over dx2. So this is definitely wrong, alright? It's also the same reason why d2y dx2 is not 1 over dx2 d2y. Because this is a further rate of change again. Now in d2y dx2 is a rate of change of the gradient, and 1 over it does not give you back the rate of change of the gradient. dx2 d over d2y is actually undefined in a sense. Alright, so now we know that the second derivative test is very difficult because you don't have to we have to differentiate with respect to x again. So let's just do the first derivative test, sine test. Alright, so we have t equals to pi over 4. Okay, so we have t pi over 4 minus pi over 4 and then pi over 4 plus. Then we have dy dx, and then we have to find the shape of the graph. Okay, 0. When t is equal to less than pi over 4, so when t equals less than pi over 4, we know that 2t will be less than pi over, slightly less than pi over 2, and it's in the first quadrant, therefore cosine will be positive. The denominator, if you realize, is always positive because e to the power of t is always positive, t squared plus 1 is always positive, and t squared plus 1 plus 4t, well, if t is positive, this whole expression will also be positive, and therefore we just look at the numerator. If it's negative, the whole thing will be negative, but in this case, numerator is positive, since the denominator is always positive for all positive t, therefore this is positive. Now, if 2t is slightly more than pi over 4, it will be slightly more than pi over 2. As such, it's in the second quadrant, and in the second quadrant, cosine is negative, so the numerator will be negative, the denominator is always positive, that's why negative. This will become a maximum point. So over here, this will be the maximum point, so in order to write down in statement, e pi over 4, pi square plus 16 over 16, this is the same as pi square over 16 plus 1 square, bracket 1 is a maximum point. Now we move on to the second point. Okay. Actually should draw my line downwards. Aha. Alright, now t equals to 3 pi over 4. Same thing here. T 3 pi over 4 minus 3 pi over 4, 3 pi over 4 plus. Below will be dy dx, and then the shape of graph. At 3 pi over 4, dy dx is 0, so we can just write that down. Now, same logic. When t is slightly less than 3 pi over 4, 2t will be slightly less than 3 pi over 2. That means it will be in the third quadrant, where tangent is positive. Therefore, cosine is negative. That's why the numerator will be negative. Denominator is always positive. For positive t, negative dy dx. Now, 3 pi over 4, slightly more than 3 pi over 4, so 2t will be slightly more than 3 pi over 2. In the fourth quadrant, where cosine is positive, numerator will be positive, denominator is also positive, dy dx will be positive in slightly more than 3 pi over 4. Therefore, you have a U shape, and as such, we can tell what the stationary point is over here, right? It's a minimum point. Hence, e to the power 3 pi over 4, 9 pi square over 16 whole thing square, bracket minus 1. This point here is a minimum point. And there we have it, the stationary point for parametric differentiation.